Alright, so let's examine that telescopic cascode, and we'll start looking at the limitations of the telescopic cascode. We already know that it's a good voltage amplifier in the sense that it has good voltage gain, but it's a bad voltage amplifier in the sense that it has high output resistance. So we get some good and we get some bad. And that's really one of the names of the game for analog circuit design. What are the trade-offs we have to make in order to achieve the goals that we're trying to achieve? So here we have our plus minus input differential voltage. We get our output voltage at this node. And we have to draw our current mirrors. And we'll connect these transistors to VB, some constant DC bias. So this is M1, M3, M5, M7, and M2, M4, M6, and M8. Alright, so what we might ask first of all is what's the maximum that the output voltage can be? Okay, so to find the maximum that the output voltage can be, we need to keep M6 and M8 saturated. And so we know that V out max is equal to a VDD we know across transistor M8 we need a VOV plus a VT. So this is a VOV plus a VT. And across M6 we need just a VOV. So if we start from the top here and subtract these voltages, we see we need a VDD minus a VOV plus a VT minus a VOV, or V out max is equal to VDD minus 2 VOV minus a VT. And I should be writing VTH, the threshold voltage here, not the thermal voltage. Now what does that condition come from? Well, I have to do KVL around this loop to this point to figure out that I need this VOV plus VT. But remember when we looked at the cascode current source, this was the requirement. Alright, now let's think about what I need for a minimum here. What's V out minimum? So here I'm going to come from the bottom, and I know that my output voltage needs to be, it can't be low enough that I cause M4 or M2 to leave saturation. And in this case I just need a VOV across M4 and a VOV across M2. So V out min is equal to, and let's assume that this was a transistor current source, I would also need a VOV for this device. So V out min is equal to, oh, and one more thing, let's call this just generically VSS, is equal to VSS plus VOV for the tail current source plus a VOV for M2 plus a VOV for M4. If all the VOVs are equal, we would say that this was VSS plus 3 VOV. That's not necessarily a good assumption, but we're just simplifying things right now. So our output voltage would have to be between these two voltages. Now the cascode bought us a lot of gain, but it also definitely shrunk the output voltage range that we can use in the device. Now, one other problem that we might have is oftentimes we want to use our operational amplifier as a buffer. So imagine we're trying to hook the operational amplifier up in the following configuration. We put our input on the non-inverting terminal, and we just feed our output back to the inverting terminal. That would be like if we shorted V out to the inverting terminal here. And this is actually a very difficult case for us. So now let's actually look at what our conditions are at the from the output voltage to keep the devices saturated. Alright, so we need to keep both M2 and M4 saturated. So let's look at our what we need on these devices now. So I know that V out here needs to be greater than, I'm going to start at node VB. I've got to have a VOV plus a VT for M4 to get to this node. So that would be VB minus VOV 4 minus a VTH 4, and then I have to go up to the supply voltage, up to the output voltage node now, so I have to go up at least one VOV, so that's plus a VOV 4. And when I work all this out, V out needs to be greater than VB minus VTH 4. So whatever voltage I set here is going to set what my output maximum voltage can be. Now let's look at the condition for the minimum voltage. So here I know I have a VOV2 that I need to worry about. So let's work through the minimum voltage. Sorry, this was the minimum voltage. Now I need to V out greater than this number. This is the minimum voltage. Now I'm finding the maximum voltage. So I can say V out has to be less than, let's call this node X, Vx minus a VOV2 plus a VTH2 plus a VOV2. And again, this has to do with the fact I start at this node, I go down through this VOV and up this VGS, which is tied to the output voltage. So here I find that V out has to be less than Vx plus a VTH2. But I also know what Vx is. Vx is just equal to VA minus, VB minus a VOV4 minus a VTH4 plus a VTH2. Now we might assume that VTHs are equal and that those would cancel each other out. But the bottom line is that what we have here is a condition where V out needs to be less than this voltage, VB minus a VOV4 minus a VTH4 plus a VTH2. These might cancel, they might not. And it has to be greater than a VB minus a VTH4. So this is a very narrow range that this can work as a buffer in, because I'm going to have to choose a bias voltage that's going to narrow the range, and the other thing is I'm going to have to size my device VOV4 to try and make that small. That means I might need to have a very large device. If I have a large device, it'll increase capacitance. So these things are going to be problematic. So the thing to think about really is, what sacrifices did we make in going to a telescopic cascode? Well, we made sacrifices in terms of what our total output swing can be. When we just in general, but especially when we hook the device up as a voltage buffer. And we did that so that we could get high gain. But when we got the high gain, we also gave up bandwidth. We have a narrower bandwidth. So in the next class, we'll start looking at what happens if we do things like a folded cascode, or we will start to try and cascade multiple stages. And we will do that next Monday.